Hi, welcome back to Introductory Algebra. Today we're doing section 4.1, multiplying with exponents. So there are several properties we're going to be looking at. So I'm going to give you a property, I'll give you some examples, and we'll do a little scientific notation in this section too. So it'll be fun. Property 1, if you have two things with the same base, okay, they have to have the same base. If they don't have the same base, don't do anything to them. When we multiply them together, we add their exponents. So a to the m times a to the n is equal to a to the m plus n. One very important note here, the base does not change. Okay, we never change the base if we're multiplying things with the same exponent. Alright, so I have two examples. First, I have a really pretty straightforward one, x squared times x to the third. 2 plus 3 is 5. That's it, x to the fifth. Now, this works because if you think about it just a little bit, x squared is really x times x, and x cubed is 3 of those. And if you just count them up, there are 5 x's. 2 plus 3 gives you the 5. Now, what happens if you have coefficients in there with your letters? So I have 4a cubed times 6a to the fifth. Well, all we're going to do here is we're just going to multiply the 4 and 6 like we would normally and get 24. And then we do the same thing we just did with our exponents. 3 plus 5 gives me the 8. Okay, so when we multiply things with the same base, we add the exponents. All right, let's get to property 2. All right, property 2. Power raised to a second power. When you have a power raised to a power, so I have 8, my base is a here with powers of m and then n, you multiply the two powers together. And so we can see it here, 3 squared to the fifth power, 2 times 5 is just 10, we get 3 to the 10th. Now normally, if you have a number to a power, you want to simplify that. I didn't here, 3 to the 10th is really quite large, but normally we want to actually figure out what that's equal to. With x, we can't do that, but we do the same thing. We do 4 times 9, because that's my power to a power. 4 times 9 gives me 36. And that's the second property. Okay, we've got, I think, one more in this section. All right, our third property says if you have multiplication inside your parentheses, very, very important, it has to be multiplication, or as we'll see in the next section, it can be division, but this never works with addition or subtraction on the inside. Okay, so I have a times b here inside my parentheses. Two things or more multiplied raised to a power. You are allowed to take your power to all the pieces on the inside, as long as it is multiplication. That's very important, as long as it is multiplication. So my examples, I have 2x squared raised to the third power. So I rewrite it as 2 to the third times x squared to the third. Both parts get that third power. Very importantly, don't forget the 2. A lot of times people forget to take the exponent to that, just to that coefficient, to the 2 here. Don't forget that. 2 to the third is 8. Here we have a power to a power, so we multiply. 2 times 3 is 6. And then my next example, 4ab squared all raised to the third power. Now, one really important detail here. This a has its own exponent. That 2, that square, is only on the b. If it was going to be on both, a and b would have to be in parentheses. So here the exponent on the a really is a 1. And that's worth knowing and worth paying attention to. So again, I take my exponent to all the pieces. I have 4 to the third, then I have my a to the third, and finally my b squared to the third. 4 to the third is 16. I'm sorry, 4 to the third is not 16. 4 to the third is 64. We have our a cubed, and then we do our multiplication. 2 times 3 gives me an exponent of 6. So the real fun happens when we start combining these, and I'll do a couple of examples of that on the next board. Okay. So here is my big example for kind of combining a lot of this stuff. And unfortunately, let's see if I can turn this just a little bit. No, I can't. There we go. That's better. Now that glare moved just a little bit to the side so we can see it better. All right. So I have 2x squared, y to the third, all of that squared, and then 3xy cubed, all to the fourth power. So I have a lot of different stuff going on here. I'm going to choose to take these in separate pieces for now, and eventually down here I'll put them together. But first I'm going to deal with these by themselves. The reason is because I have this whole thing with a power on it, and this whole thing with a power on it. And so I can't try and combine the two until I deal with those powers on the outside. All right, so you can see I use brackets here to try and keep everything together. But I have my 2 to the second, I have my x squared to the second, and my y cubed to the second. Came over here and did the same thing. 3 to the fourth, x to the fourth, y cubed to the fourth. And then I'm going to clean up those messes a little bit. 2 squared is 4, 2 times 2 gives me x to the fourth, 3 times 2 gives me y to the sixth. On the other one, 3 to the fourth is 81, just x to the fourth, and 3 times 4 gives me y to the 12th. Finally, now I'm multiplying. So 4 times 81, that's just regular multiplication, gives me 324. Now, remember, power to a power, we multiply. But when we're multiplying, we're going to add those exponents. So 4 plus 4 gives me x to the 8th, and 6 plus 12 gives me y to the 18th. There you go. That's a big, messy example. Hopefully follow that. Go back, watch it again if you need to. Now we're going to look at some scientific notation. And that'll be it for this section. All right, so now we're going to look at scientific notation. Scientific notation is going to take very big or very, very small numbers and write them in this form. A times, and this x is actually a time sign, a times 10 to a power. So a few things we need to know here. A is always a number between 1 and 10. Well, or between -1 and -10. And n is the number of spaces we're going to move the decimal point. Okay, because what we want to do is we want to take these very large or very, very small numbers and basically cut out a lot of zeros. Case in point here, you can see I have 3 billion. It's a very large number. One other thing though, if we move the decimal point to the left, we get a positive value for n. If we move it to the right, we get a negative value for n. So I have 3 billion. Now, in 3 billion, the decimal point is actually sitting way back here, right? There was no decimal point in the number, which means it's got to be at the end of it. So I know that to get a number between 1 and 10, the decimal point is going to have to go after the 3. Here's a hint. It always goes on the right-hand side of the first non-zero digit. So there's my first non-zero digit. The decimal point is going to go right there. That gives me 3, which is between 1 and 10. So 3 times 10. And then all I have to do is count how many places we had to move the decimal point to get it there. So 1, 2, 3, 4, 5, 6, 7, 8, 9 places. 3 times 10 to the 9th power. And this is good because for scientists, when they're working with exceedingly large or very, very small numbers, it takes away some of the computational errors because that's a lot of zeros, and sometimes they have even more zeros than that, which can make it very tricky to get the right answer because if you leave out a 0 or add an extra one on accident, you get a wrong answer. My other example here, 0.000000012, a lot of zeros again. So now I have a decimal point that's obviously here, and I'm going to aim to put it after my first non-zero digit, right? After that 1, in between the 1 and the 2. So that I'm going to have my 1.2 times 10, and now I have to count. 1, 2, 3, 4, 5, 6, 7, 8 places. This time I went to the right, though, so I get a negative exponent. Now, it's important to note we can go the other direction. We can go backwards. But just be careful because a positive exponent, if you're going backwards, is going to send it back where it came from, back to the right. A negative exponent would send it back where it came from, back to the left. So anyway, that's scientific notation. I do have one more example that I want to do with it real quick for you. So let me get this board cleared off. We'll do that last example, and then this video will be all done. All right, so this last example involves multiplying with scientific notation. So I have 9 times 10 to the 15th, there's my first number, and I have 8 times 10 to the 20th, my second number. The reason this is in this section is because, quite simply, this is exactly what we were doing with some of those problems with exponents before. I'm just going to multiply 9 and 8 to get 72, and since I have two things here with the same base, those 10s, I add the exponents. 15 and 20 make 35. Now, this is really close to being the right answer. It's not quite there. The problem is that 72 is no longer in scientific notation. So since we started with scientific notation here, we really want to end with scientific notation. 72 is too big, right? It needs to be 7.2. I need to take that decimal point, slide it one more place to the left. All right, again, that decimal point, if it's not there, is always at the end. I'm going to slide it one more spot to the left. All right, so I slide it one more place, that gives me 7.2, but because I went one more place to the left, the exponent has to go up by 1. And that's how I get 7.2 times 10 to the 36th. So there you go. That's some basic scientific notation and multiplying. In the next section, we get to look at division. It'll be fun.